Unlike TCP, Quick UDP Internet Connections or QUIC encrypts almost everything, even control headers. This breaks most existing IDS tools, leaving defenders blind. Security analysts can no longer inspect key traffic patterns, so the question becomes, can we still see enough to act? Our goal was to create a Python-based toolset that captures and analyzes quick traffic in real time, not by decrypting, but by using the limited metadata still visible in packet headers. We also simulated attacks to test if detection was even possible. We used AI QUIC for client-server QUIC communication, Wireshark for visual inspection, and Scapy to craft and monitor packets. Everything ran in a controlled Linux-based test using QUIC-enabled browsers and Python scripts. Our test environment included two Kali Linux machines, one acting as a QUIC server and another as a simulated attacker or client. The server ran AI QUIC with a self-signed certificate, and Chrome was configured to support QUIC for browser-based tests. Let us now examine the full solution architecture from both the attack and detection perspective. As represented in the diagram, we begin on the left with the QUIC attacker. This component initiates four categories of targeted traffic, each designed to stress a particular aspect of the QUIC protocol implementation on the server side. The first attack is the QUIC initiate flood. Here, the attacker sends hundreds or even thousands of initial handshake packets to the server within a very short time window. Each packet uses a unique destination connection identifier or DCID, which tricks the server into thinking these are new connections. Since the handshake is never completed, the server continues allocating resources, leading to potential exhaustion. This simulates a DOS or denial of service condition. To detect this, our monitoring tool applies a time-based heuristic. It watches for any source IP address that sends more than 100 unique DCIDs within a 1-second interval. If that threshold is crossed, the system immediately raises an alert for a suspected initial flood. This alert not only captures the offending source address, but also the number of attempts and timestamps, helping us isolate the source of attack. The second is the fake zero round trip time request. Normally, QUIC allows clients to resume connections quickly using cached credentials from a previous handshake. However, this shortcut should only be used when there is a valid session history. In our attack simulation, the client sends a zero round-trip time packet without ever completing an initial handshake. The goal is to bypass an authentication and trick the server into treating it as a valid resume session. Our monitoring logic detects this by keeping track of all DCIDs sent in a valid initial packets. When a zero round-trip packet arrives, it compares its DCID with that list. If there is no match, the system flags it as a mismatch and issues an alert. This helps us catch replay attempts and improper session resumptions that deviate from the protocol standard. The third attack is version forgery. The QUIC protocol requires that both client and server agree on a supported version to establish a connection. In this attack, the client deliberately sends initial packets with forged or unsupported version numbers. The aim is to confuse the server's version negotiation logic, possibly forcing unnecessary fallback behavior or consuming processing cycles or invalid negotiations. To defend against this, our detection engine maintains a list of recognized QUIC version codes, including those defined by the IETF and Google. If a packet arrives with a version field that falls outside this known set, it is flagged as a forged version attempt. An alert is triggered, and that includes the forged version, source IP, and timestamp. The fourth and final attack is the malformed QUIC request. In this case, the attacker deliberately crafts packets with broken or invalid headers. These packets may have missing fields, incorrect length declarations, or completely misaligned byte structures. This is a classic fuzzing technique used to crash a destabilized protocol passes. Our monitoring script addresses this by performing structural validation on each QUIC packet that checks whether the headers contains the required field and the length and positions conform to the QUIC protocol specification. If the packet fails these checks, such as having an invalid connection identifier length, for passing, the tool raises an alert for malformed QUIC traffic. In summary, each attack type is immediately followed by a corresponding detection mechanism. The QUIC initiate flood is matched with volume-based anomaly detection. The zero round-trip time fake request is countered, and with session history tracking, version forgery is addressed by validating against known protocol versions, and malformed packets are filtered using the strict structural validation. All of this occurs within a real Python monitoring script using packet capture via Scapy and header passing logic tailored to QUIC's protocol format. By focusing on unencrypted metadata fields, we ensure that no private or application layer data is exposed, keeping the analysis privacy compliant. This architecture gives us the confidence that even without payload decryption, modern protocols like QUIC can be monitored effectively using lightweight heuristic-based telemetry.